this is our A, and this is our B. And now I'll be plotting our vector polygon. So let's go. We start from here. This is our origin, starting point. Remember I said starting point, never took it very close to here or close to the top. You take in the center point so that all around it you have space. And now the first thing we need to do is scale. So let's go scale. 10 millimeter per second square equals 1 millimeter in our graph paper. Graphical solution, no scale, no solution, zero, automatically zero. Automatically, no question answer. Because it has no value, nothing, you can take. So now, first thing, which parameter we have first? Look at here, we'll be starting like building a house. I always say, graphical method is like building a house wall. One brick, and the top another brick, and the top another brick, and the top another brick. You do not go from the one brick and all of a sudden the top layer. No, step by step. Same thing also here, hey, young people, look at the first thing. As we wrote the equation, we will be always writing in our sequence our AAN, and then where our AAN finish, our AAT will start from there. Where our AAT will finish, our ABAN will start. And where our ABAN finish, our ABAT will start. Clear everyone? That's how we'll be doing. So now our first thing is AAN. So we have our AAN. It has how many letters it has? Only one letter index. N is the coordinate system it shows. It is not our letter. It is a letter, but it is a different meaning. We'll be looking at only what is our here on this side, what letter is there. So our A1, it is the one letter, it is the absolute acceleration. Of course, absolute normal component. And also it has the link of connecting rod, it is the link of crank, which is the connection with the ground. So therefore it should start from where? From here. And how it is directed? From A to O. And now using our that scale, what is the length of it? Because it is 100 millimeter, we divide it by the 10, it becomes 10 millimeter long. 10 millimeter long, but 10 millimeter is too small. So when you draw it a little bigger. And I cannot draw it in 10 millimeter, you will not be able to see it. So I do a little bit longer and simple. So what I do? Where is our paper gone? Ruler. Let's go to find the ruler. This is our ruler. Some of you are a little bit surprised that it is a why it didn't become ruler, because it is a more or less rectangular thing. Okay? I need only this thing, nothing else. Only when I plot this one, I need to draw position correctly. And now have a look how I do. Hey, young people. And I come like that. Come like that. And of course, with this putting, and parallelly I move it here. Let's see how I did. How many seconds it take? Only few seconds. Again I do it. Have a look how I did. My objective is to draw our AAN parallel to A to O, correct? And 10 millimeter length. So I take this one, look at here how I do, and then how I do this one, and how I do this one, and how I do this one. You need to move parallelly, and then you come here, and then you do like that. Clear to everyone? So I am now writing this one. So I show here parallelly, approximately. This is our 10 millimeter. And look at here, starting from our origin, 10 millimeter finish, I finished with an arrow. Can you see that? Continuous line. Why continuous line? Because we know its value. And I gently, here I write, this is our AAN, parallel to A to O. And then I have also another interesting thing. What is that? We do not have our AAT. AAT value is 0, correct? Look at there. So therefore, this one equals what? Absolute AA. Absolute AA. Okay, and the second component, when we are asking, second component, our AAT, unfortunately, our AAT is 0, because if it was, then it should be perpendicular to it, like that. Clear to everyone? It will be perpendicular to it. As it is going, rotating, it is rotating this way, so therefore our AAT will be going this way. Clear to everyone? It follows the angular acceleration direction. Alright, now, so we finish our first parameter we draw, second parameter unfortunately 0, and our ABAN. So unfortunately our ABAN will be starting from the tip of AAN because our AAT equals 0, that's what. How it is directed? Also we know its value. But unfortunately, I didn't put it here, that's why you don't know how many millimeters. Is it 10 millimeter or 20 millimeter, we don't know. But we know its value. So, how it is directed? Look at here. It is directed from B towards A. So, what I'll do, look at here, from B towards A. So, I'll be coming here and I'll be drawing here. I'll be drawing here. I don't know, it can be big or small. So I'm writing here, say it is up to that point, not to make very crowded. And that is our ABA and parallel to B2A. Write with the pencil first. Don't write with the pen. First time when you write this letter on the side, you do not write with the pen because sometimes your next line can go on the top of this writing. So if you write with a pen, it will be a little bit difficult to erase it and to write somewhere else. So write first when you draw with the pencil. Okay, we finished this one. And now the last parameter left, what is that? Our ABA tangential, right? And ABA tangential is the 90-degree angle of our AB, like that. Look at here, like my leather pointer I'm showing you. If we use this beautiful thing, it will be like that. It will be like that. 90-degree angle of it. Clear to everyone? But from where it will start? Where our ABA and finish at that tip. So what I do? Look at here how I do. This one, I bring it. Look at here again. And I draw. Because it will be straight line, because on the side it's difficult to see. So this one is our ABA tangential perpendicular to AB or BA. This time you don't need to follow B to A or A to B because it is nothing to do with it. It's just 90-degree angle of it, that's all. And now have a look. I draw your attention a small little careful thing. Your normal and tangential, they are perpendicular. This normal and this tangential, so this angle should be 90-degree angle. If it is not, then you did not align properly. Clear? And now have a look what I did. Because our ABAT can go this direction, it can also go this direction as well. Clear to everyone? I only said it is a 90-degree angle. I did not say which way it is going. It is our ABAT going up or going down. I only say it is 90-degree angle. So information is half information, not full information, correct? So that's why I draw a dotted line. Dotted line, it means I don't know its value. I know only its line of action, which direction it can go. So it can go from here to that direction. It can go from there that direction. That's why I put a dotted line passing through the tip of where our ABA and finished. Clear to everyone? And I cannot do anything on the right hand side. And now only parameter left on the left hand side is our AB absolute acceleration of the piston B. And it is a 1-letter index. And also it is a link that has connection with the cylinder wall, ground. So it should, from where it should start? It should start from the origin of the vector polygon, from here. As I said, I wrote down all these things for you, particularly those who came a little bit late. You remember yesterday we talked about that, and that is this one. Everything is written here. Okay? So you don't need to memorize these things because you will forget. But what you do, you print this one, this page. I'll be uploading this one because yesterday's first part I already is available in Canvas. Most probably you saw it. Okay, so those who haven't downloaded, you download it please, because some of your classmates already downloaded this evening. And this one I'll be putting today. And the other two parts I'll be putting tomorrow before I leave for Melbourne. All right? Very important. So now have a look. So it should start, our AB absolute should start from the origin, starting point here, from here. Now, we only said in our equation, we say that it is parallel to the horizontal direction. So it means from here it can go to the right, from here it can go to the left. Clear to everyone? As per our equation symbol here. That symbol is here. Look at here, symbol is here. AB parallel to XX. I did not say it is going to the right or going to the left. So, but it is definitely horizontal. But it should start from here, from the origin. So therefore, let's go. We do it. So how I do it? Parallel. I take this one here and I bring a line here parallel, horizontal direction. Easy. So what I do? Look at here how I draw. Look at here, all of you. I draw a horizontal line to the left because as I am not a god. And from here, it can also go to the left as well. So therefore, I am from here, a dotted line, I am continuously putting that way. It's a straight line. Young people, a little bit of curve. You forgive me, I'm an old man. That's why it's happening. Here, you put a ruler and then put the dotted line. So now, and here, as I am, we need to say what is it? It is our line of action. A, B, parallel to X and X. And now, we are all scratching our head together. What is it? We are looking at our equation. Because, as I said yesterday, you have 2 points you'll be looking at. One point is the equation, and other point is the vector polygon. Your vector polygon, your equation here, it clearly says that it should be closed. Clear to everyone? This vector form, it will be closed. It is not open. Now look at here very carefully. This red dotted line is a line of action where our ABA tangential should be. On this line, starting from our ABA and from the tip, it can go down or it can go up, correct? And our absolute AB of piston B from our origin, starting point, origin is the starting point of the vector polygon, it can go to the left or it can go to the right. But it should be on this line. It cannot go any other line. On this dotted line somewhere it should be. Okay? So now, if our ABA tangential goes downward, look at very carefully, if it goes down and our absolute AB goes to the left, then it never closes the vector polygon. All lines intersect. That's called closed. So therefore, if our ABAT comes from here upward, look at here very carefully how I determine this. From here, if it goes up, and our absolute AB, from here it goes to the left, then only it crosses the all line, intersects. Clear to everyone? There is no other way. There is no other way this equation will be closed. That's why I told you, you keep 2 points to your eyes. Vector polygon and equation. Your action is correct or not, it will tell you. So, we say, aha, we found our bingo. $1 million lottery. I put a little dot here. That is our point of interest. Now we can say with 100% confidence that our ABAT will be, now look at how I draw. Look at here. Your computer, those who are doing the SolidWorks, it will not say any of these things. Because you are dictating SolidWorks how to draw, not SolidWorks to you. So, from here now what I do, have a look. From here, I do continuous line up to that point where it meets our absolute AB. That tiny one is our real ABAT tangential value. This dotted line have no value to me now, and this dotted line has no value to me now. Clear to everyone? And then from here, I make the continuous line up to that point. That is my real absolute AB. And from here on that line, dotted line has no value to me now. And from here up to there, that direction, dotted line also has no value to me now. Clear to everyone? Hey, young people, look at very carefully. There's something interesting thing is happening here. In our velocities case, yesterday we did it. Look at here quickly. In our velocities case, our velocity, young people, look at here. In our velocities case yesterday, our vector velocity VV is going to the right. And our acceleration case, absolute acceleration case, our acceleration AB is going to the left. There are something is terribly happening here. And that things will not tell you analytical method. Only graphical method can tell you every possible information you need to know of the motion. Anyone can tell me why it is happening, young people? The velocity is going to the right and our absolute acceleration is going to the left. The reason is your piston. Hey, young people, at the moment our piston orientation is horizontal. It can be also vertical as well. Automotive engine is vertical orientation. So, look at here. Our piston comes up to the extreme left from my side. Say, if you start extreme right, and then after that it cannot go further. And then it go down. When our A is somewhere here, our piston will be extreme left. Clear? And when our A crank position will be somewhere here, it will be our piston will be extreme right. Correct? Look at very carefully. And extreme right, when it is, we call top dead center, or in our case, horizontal dead center to the right, and horizontal dead center to the left. Clear to everyone? In our normal, in car engine case, we say top dead center, bottom dead center. So how it is moving? Look at here. If you consider, here is a piston, here is my crank, and this is a connecting rod. Right? Right? So, and now when our piston, look at our piston, don't worry about connecting rod and the crank. Piston is going like that. And when, look at here, when it goes like that, very fast, and when it is going to the top dead center, if it is going all the time same speed, and all of a sudden it cannot stop to go reverse, it will be big shock on our crank and the connecting rod. Get everyone? So when it goes very close to the top dead center, it need to be slowed down. So therefore, what is your acceleration AB? Your acceleration AB, that's why young people, dynamics that you did in entry course, very vital. Our acceleration A equals V minus U divided by T. And this one is your final velocity. When you are coming to the top dead center or bottom dead center, this one is a smaller than initial velocity in the middle. So as this one is smaller than this one, it becomes negative. And it is not zero, it is negative. It means if you have this one, if this one, say, this one is say 10 meters per second square. And this one say close to top dead center, say 2 meters per second square. So it will be what? It will be 2 minus 10 divided by T, whatever these things, and here it will be minus 8 by T. And if T is taken that 5 seconds or 2 seconds or 1 second or 0.5 second, you can find your acceleration. So it means your piston is close to the top dead center on extreme right. Clear? That's why it is slowing down. That's why your acceleration reverse direction. Because it's a negative value, it means vectorally it is opposite direction. Dynamics, it is not a pure mathematics, it is not a mathematical purity. It is everyday life, everyday machinery, everyday mechanism. So I draw your attention, do not memorize anything, try to understand it. And I did not say anything theoretical. Everything I said to you, what is going on in practical. Again, look at here. Piston is going, when it is going, it cannot go same speed and all of a sudden it can go reverse. No way. So when it is going to limit here, it goes slightly slow and then it starts to go. And then it starts slowly and then it starts to faster. And then when it goes to bottom dead center, close to it, it also slows down. And then it starts to reverse. Clear to everyone? Because it cannot go, look at here, it goes there, all of a sudden like that. No, it will be huge pressure on the connecting rod. And connecting rod will use vibration and also it will break it. We call fatigue line. So this picture is here. Now one more thing we can do here. One more thing. Hey, look at here, young people. Unfortunately, I have a 3 color. I cannot do anymore. In Melbourne, usually I have 10, at least not 10, and 8 of them. Different color I buy, so I can draw. So now have a look. Here we have this one. We have a normal component of AB normal, and this one is AB tangential. So therefore, if from here I draw a line up to that point, that is your absolute relative ABA. Because that is your normal, that is your tangential. So therefore, from here up to that point, that is your absolute relative ABA. Because I want graphical method minimum calculator to use. And what do you need to do? You need to measure that length, multiply with your scale 10 millimeter, you get the value. Otherwise, young people, you have to use your high school math. Your absolute AB. Look at here. If you don't use that from graphical, absolute ABA, you have to use square root of ABA and this value from here up to that point, ABA and square, and then ABA T, and that value is square, and that is your ABA. So now you like this beautiful math, or you like measure from here to here and you multiply with your scale, you get with a fraction of a minute. Up to you. Up to you, young people. Which one you want to use? And you are wasting your time. Not only math, there is a possibility you will be making mistake also. But I will be doing from here. And now, one thing. There is another reason why I did it. Young people, we are human beings. We always can make mistake. But our objective will be to cross-check and eliminate if any mistake we make. That is our objective. Clear? So how we eliminate it or how we minimize it? By checking our equation with the vector polygon. Clear to everyone? So let's go. Same thing I draw it here. Let's go. We do it. Our AAN. Our AAN is this one. Plus AAT. Unfortunately, our AAT is 0. And then ABAN. This is our ABAN. And then plus ABAT from here up to that point equals AB, which is from here to here. So in our expanded equation, it says we draw everything correctly. And now we also say a little unexpanded equation is here. Short equation. We also need to check that one too, whether we did everything correctly or not. Young people, how we check it? Look at there. Our AA, and hey, have a look. From here, this one is our AAN, correct? And our AAT was 0. So what I wrote here? Why I wrote it? To cross check. So this one is essentially our AA absolute, that value. Plus ABA. And that dotted line is our ABA with the arrow. Equals absolute AB. So we also, in our short abbreviation, that equation also we have done correctly. Is it clear to everyone? Look at here. Our AA, this is our AA, ABA equals AB. Our first equation. In acceleration case, you need to cross-check, young people, both expanded version as well as the short version equation. Short version, it means with the normal and tangential we combine already. That is our this equation. Okay, and now what are the things we can get from vector polygon? Look at here. We get from here up to that point, that line, I will be measuring the length, multiply with our scale, we get our AB tangential part, and from here up to that point, we'll be measuring with the ruler how many millimeter, multiply with our scale, we get our absolute AB, which is here, and then from here up to that point, we can calculate how many millimeter, multiply with our scale, we get our absolute relative ABA, and then we can find also our angular acceleration of this length, because ABA tangential, I think I wrote that equation somewhere. Okay, I deleted it. So our ABAT equals alpha AB, the angular acceleration of the connecting rod, times the RAB, which is the 400 millimeter, and from there we find our alpha AB of the connecting rod. Everything done with a fraction of a second. Now, is it clear to everyone how we did it? Okay, if it is, let's go move on to next, because we are running out of time. Now, as yesterday we discussed that, yes, please.
How about the plus minus? Can I say AB is minus?
Usually we don't
BA
say
plus.
it. We don't say it. The reason is why we don't say the minus, because in our vector polygon clearly shows the direction. Okay?
So when we sum, it's just sum.
You don't need to minus. It is not.
It's just
If we put the value for the balancing purpose,
yeah.
then we need to write it is the negative in that direction. And your balancing force, you need to put opposite direction. So your force that will generate at that instant, on the piston shaking force will be in that direction. You are right. It will be in that direction. So to balance the piston, we have to push opposite direction a equivalent force. But we don't need to write minus.
For this case, when I sum, I just sum at the bottom.
Yes, you need to. You can write in word. That's it. Don't need to write. You need to write here that in our velocities case, it was going to the right, and our acceleration is going to the left, means our piston is slowing down. That's all. Yeah, pure engineering work. Pure engineering work. Clear? That's the thing you will be writing most of the time in report. You will not be writing -8. Okay? All right. Now this one, example 2, I will not be spending a lot. Here only difference is we don't have a piston. We don't have a piston. Clear to everyone? Hey, look at here. Before we do so, yesterday we discussed that we will have a little break at some time. Yesterday, when we had the break? God, I am really falling terribly behind. I need to go now, not only the speed of light, even more than speed of light. Alright, we'll have around say 10, we quickly finish this one, and then we'll have a break, okay? And we'll have around 20 minutes, 25 minutes break, because I saw yesterday some of you take a couple of minutes more. So we'll make it around 25 minutes, so that those who go outside and have food, but don't eat a lot of food, otherwise you'll fall asleep. Okay, now, this one, look at it very carefully. I will not explain everything in detail. Hey, look at there. First I explain the mechanism. The mechanism, it is also a 4-bar linkage mechanism. Our OA, AB, and this one is our closed loop. So look at here. Here I explain to you that our OA is a pure rotational motion in relation to O. Our this BC or CD, it is the one link. Young people, it is the same link. Clear? And that link also rotates in relation to point C. So our link 2 and link 4, this is the link 2, this is the link, this our AB is the link 3, and our CD or BC or whatever you want to say, that is our link 4. Clear to everyone? And ground 1 and ground 1 here. And look at here, young people, every time when I draw it, from where I started? From where I started? When I draw this linkage, I started from the ground. I put this one symbol, and then I put that line, it means it is a ground. Clear to everyone? If there is not this symbol is here, it is not clear, it is a ground, or it is hanging in the air, or it is flying 10 kilometers above the ground. Not clear. Is it clear to everyone? Symbol need to be correctly done. And your SolidWorks doesn't do that. You need to do it. So, and then from here I draw this line. Of course, the angle you need to put, whatever angle is given, in our case maybe 45 or something. So, and then you go accordingly. So now, here our BC definitely going general plane motion, because it will have a both rotational motion, curvilinear rotational motion and curvilinear translational motion. You can clearly see it. And how it is happening, you can check it later. So now our objective is to find the velocity at point B, velocity at point E, velocity at point D, velocity at point F, and also acceleration at all these beautiful positions. And it is a little bit of time consuming work, but it's essentially absolutely not difficult at all. What is why? Look at strategy. Strategy engineering is more important than anything else. Look at here. Don't look at all these scary points. I told you to find velocity at point B, velocity at point E, velocity at point F, velocity at point D. Remember all I said? You ignore all of them. Only you look at OA, AB, and BC. Other things automatically will come later. Clear to everyone? You do not look at other position E, F, and D, and for the time being, you forget about it. You consider your link is OA, AB, and BC, and OC is a ground. OC is a ground connection. It is a 2 point on the ground fixed. Clear to everyone? Like it is a floor. So, our life is easy. The most important thing is we don't have a slider. So what I will do? We will write our VA, because now here I tricked you. Here I tricked you. How I tricked you? Here I did not give you the opportunity to assume that omega 2 is constant. Clear to everyone? What I did? I also showed the angular acceleration. So it means you cannot assume this time your omega 2 is constant. Clear to everyone? So it means here your AAT is not a zero. Like our crank connector and piston mechanism, our AAT was zero because omega 2 we assume constant. As I did not give you the value. Clear to everyone? So from there, what we did? We found our VA equals omega 2, that we did, and 100 millimeter. And of course, VA is a 90-degree angle because omega 2 is rotating anti-clockwise. Our VA will be going. Look at here how I showed. Can you see how I look at here every time? I follow the same pattern, same symbol, same approach. I did not do anything different unless I forgot something. Why I do it? I am telling you all the time same thing, repeating, same process. And I am not making any shortcut. If you do shortcut, all the shortcut will be leading to a disaster. Maybe at one time you will win, nine times you will be losing. Don't use shortcut. You always do the process correctly. Shortcut, generally in engineering, will lead to a disaster. Now have a look. I showed here VA, and then I wrote, because first we need to find out the velocity. So our objective at the moment, we ignore point E, we ignore point D, we ignore point F. These 3 points doesn't exist to us. We are looking at pure formal linkage mechanism, and the joint is, the linkage connection is OA, AB, BC, and OC. OC of course is the ground, it doesn't have any velocity, nothing. So we write our vector equation. Young people, have a look. I go there. Usually in Melbourne I do not sit on the table, but here you are sitting on the corner, that's why. So have a look. In our here, I write exactly the same approach. Yesterday I showed you relative motion. Remember that? So the velocity at point B will be velocity at point A plus velocity B relative to A. So I wrote this, and look at here, very correct. Using relative motion, we write. Using relative motion. Every time I'm writing how I write that equation, from where all of a sudden this beautiful equation appear here. Is it come from the sky? Or is it come from somewhere else? How this equation? I also write in the previously, I wrote that equation in a vector form. Remember on the side I wrote in the previous equation, previous our example? So I always write using relative motion in vector form, or vectorally we can write this equation. Because it is not a arithmetic sum, it is a vector equation. Please write it. If you do not write it, you allow to create a confusion in you. You allow to create a confusion in you. That's why I write it. So now, we wrote it, and now, hey, we have a 3 parameter. We need to ask the beautiful question. What is that? We know its direction, but we don't know its magnitude. So let's go to ask first question. BA, do we know its direction? Yes, it is perpendicular to our OA. I also showed you with the symbol here that rectangular, and then in the middle dot, it means 90-degree angle. You learn in high school that symbol. I believe in Singapore you use it. But if you did not use in Singapore, then God bless Singapore. Okay, that's the only thing I can say. I cannot say anything else because you have so many tall buildings, per capita income is more than $80,000. What I can say to you? Only God bless you. All right, now young people, we know its direction and how it is directed. 90-degree angle to our OA or perpendicular to OA. Do we know its value? Yes, it is 100 millimeter per second. So therefore I wrote also another beautiful underline, you can see it, but different color. But this time I used, unfortunately, other color, not red one. So otherwise you all of you say, oh, Professor Firoz all the time use red, I have to also use red. No, you use different color but consistent. Clear to everyone? That's my message to you. And then the relative velocity VBA, B relative to A. How it is directed, young people? Do you know its direction? Yes, we know its direction. How? And that's the Bible again. We did it yesterday with that problem. Remember? Hey, don't forget about it. Our relative velocity VBA is a 90-degree angle to that link. And also I said one beautiful word. I said, from now on, you learn all the relative velocity with two-letter index. They are always perpendicular to their respective link. Clear? I showed you here. Many of you at the time didn't realize why I said it is a little Bible. The graphical method, this is the most important thing. All right, so we write here, yes, we know it's your direction. You are 90-degree angle of A, B like that. Clear to everyone? It can go up or it can go down. We don't need to worry about. Our vector polygon will tell us exactly which way it's going. So we wrote it here. One underline. Unfortunately, we don't know its value because we don't know omega AB. That's why the problem. So we leave it. Our second underline is not there. I wrote it as a perpendicular to AB. You can say AB or BA, it doesn't matter what you write here. And then we come back to our absolute velocity at point B. Now, absolute velocity at point B, it is the rotational motion of that link. Which link? Of that BC or CD or CF, whatever you say. It is a one link starting from here up to that point. How it is rotating? Look at here. It is rotating like that. Clear to everyone? Exactly the same way as your OA is rotating in relation to O. Clear to everyone? And that's why your velocity VA is a perpendicular to OA, is a rotational motion. And therefore direction of VB will be determined by the rotational motion of this link BC. So therefore it will be 90-degree angle to BC. And that's why I have written it is perpendicular to BC. Clear to everyone? As our VA is going this way, our VB should go also in that direction. Our logic says. But we don't need to worry about that. Our vector polygon will tell us exactly what's going on. Logic is a cross check with our vector polygon. Clear? Because many of you did not realize how powerful the graphical method is. It requires minimum memorization. It does not require any calculator. With high school, primary school, your basic arithmetic, you can solve it. How? We know that this one we will measure with how many millimeter, multiply with our scale. That's the things we learn in the high school, primary school math, even not high school. Clear to everyone? So that's the beauty of the graphical method. It is our real engineering tool. So now, have a look. We finish. It's perpendicular to BC, but we don't know its value because we don't know rotational velocity of this link. And now we plot our vector polygon. We plot our vector polygon. So how we do? We need to select a scale. In that scale, you can select any one which suits you. But always try to make the scale as big as possible. Because if you make very tiny vector polygon, you will make a lot of error. This error is not your calculation, your mathematical error. It is error of your scale error. Because you are missing some point. So now, this is our origin. And from origin, using our scale, I think I wrote somewhere scale here. You see how? Even I wrote in bracket, in graph paper. I don't know, young people, how detailed I can write. Every possible information here. And now have a look. This is our origin. and it is a 90-degree angle. So what I did, from here, I draw it. This is my length of 10 millimeter, and I finish with the beautiful arrow. And our BBA, that one will start where our BA finished. Clear to everyone? And our BA finished here. So our BBA will start from the tip of BA. It can go this way or it can go this way. Of course, it will be 90-degree angle of AB. Clear to everyone? So that 90-degree angle, you bring it this way and you plug in here. This way dotted line, this way dotted line. As we are not a god, we don't know which way it's going. If God exists. If not, that's a different thing. So, with due respect for people, those who believe God or those who don't believe God. So, it is up to you to take a decision. I don't want to say it. And that line, I wrote BBA perpendicular to AB. Now, look at here another interesting thing. You see how many times I am writing that things? I wrote everything nicely in the equation. And then, when I draw the dotted line or any line, I also write very close to it again. And that helps me to cross check. When I construct the vector polygon, I am doing everything rightly or not. Did I make any mistake? That allows me to cross check quickly. And now, and then our final velocity BB. And final velocity BB, from where it should start, young people? From where? This young man says from the origin. Yes, absolutely. It should start from the origin here. And also look at here, I also wrote a little O. This O has nothing to do with this O. It is the O, it means origin. From here it will start. Why? Because it has connection with the ground at point C. Yeah, that link. And also it is a one letter index, maybe. It should start from here. How it is directed? 90-degree angle of AB. So it is directed 90-degree angle of AB. Clear to everyone? Not AB, sorry, my apology, the BC. It will be perpendicular to BC, which I have written here. So what I did, I draw, because as I don't know from the origin whether it is going this way or this way. So I do draw a dotted line from here up to that direction and from here up to that direction. And gently I wrote BB perpendicular to BC again. And now I am scratching it. This is our dotted line. Don't worry at the moment this continuous thing, okay? Don't forget about these things. Consider it as a dotted line. Remember how I did step by step? You are seeing it final one. But I start first dotted line. Remember that how I that made? So if I show this beautiful PowerPoint presentation, you miss an important part. How I made that one continuous. I showed you. So consider this is a dotted line, this is a dotted line. And if this BBA from here, from this point it goes upward, and our BC from origin it goes this way, it will never close the vector polygon. It can only close the vector polygon if our BB from the origin it comes this way, and our BBA from the point of at the end of BA it goes downward, and then this dotted line and this dotted line will intersect at that point. Clear to everyone? And they will close the vector polygon. There is no other way it will close the vector polygon, as our equation says. And then I say, aha, we found our magic. We found it. We found exactly how much our BB and how much our BBA. Our BB, from here, it will come up to that point where it meets our BBA. And our BBA will start from the tip of BA, it comes all the way up to that point where it meets with the BB. Clear? And then what I did, young people, look at here. From here, I made continuous line, that dotted line, that section. From here up to that point is a continuous line with the arrow. And from here, look at here, I also put a dot here. From here up to all the way up to that point, this way, up to that point, continuous line. and I left this one, I have nothing to do with it, and this one I have nothing to do with it. This one I have nothing to do with it, and this one I don't have anything to do with it. Clear to everyone? If I see anyone plotted this graph without that dotted line, you do not understand anything. Because you cannot be superhuman and exactly plot that one. And that I don't need anything. I only know that you did not understand the problem. Clear now? And now we are coming back. We are coming back. Some point we forgot about it. Young people, remember? Some point we were asked to find the velocity at point E in the midpoint of AB. Correct or not? And also we were asked to find at point D at point F. We will be now looking at those points. And that's how I will be tricking you in the exam. Because I will not be able to trick you in principle because you already learning everything. So now have a look. Now have a look. This E is located, I didn't make it complicated. This E located on our relative velocities line AB at the midpoint. So what do you need? Because I asked you not the relative velocity at point E. I asked you absolute velocity VE. So what do you do? This is from here, look at here, from here up to this point, this is entirely your VBA, correct? Hey, look at here, that is your entire VBA, correct? And you go exactly in the midpoint of here, on this line here. And then from the origin you connect that line, that is your absolute velocity VE. It takes 1 second. It takes 1 second. And now, you don't need to show anything in the graph. You need only this VB from here to here, right? Hey, look at here. And that VB equals omega BC times RBC, correct? Look at here. Your VB here equals, you got it from vector polygon, right? You measure that length, multiply with the scale, you get the value. Yes or no? Yeah. And then to find at point F and at point D your absolute velocity, I am writing for you. At point F, BF equals omega, the same link because it is rotating with the same angular velocity. With point F, point D, all are in the same link, correct or not? So therefore, it will be omega BC times RCF, that length, and what is our BD will be omega BC. But okay, like that. Do process correctly, so that you will not have confusion. We write here formula BD equals omega CD times RCD to be consistent with the symbol. And here, don't write BC, you write omega CF times RCF. And here, we'll come in a second about these two equations. You write VB equals omega AB, omega BC times RBC from B to C, from B towards C, that length. You are talking about that length, from B to C, that length. And now, hey young people, from here you find your beautiful omega BC. Omega BC equals VB divided by RBC, correct? And now you say as point F and point D all belongs to the same BC link. Same link is rotating, it cannot rotate. Point CF is different direction, different rate, and CD different rate than our BC. Clear to everyone? Otherwise it will be twisted, breakdown. So entire link starting from C up to D, it is, look at here, it is rotating like that. With the same angular velocity, BC. Is it clear? So you write, as our F point and our D point are located on the BC link, which is rotating in relation to C, therefore, omega BC equals omega CD, omega CF. That's all. Omega BC, now look at here, omega BC equals omega CF equals omega CD. That's all. You solve the problem. That's why I said you, for the time being, you ignore your C, your F, your D, and your E. Why I ask you to ignore? Clear to everyone? That's all. All right. So after that we'll stop now. In fact, I can also show you all the value here as well in the graph. So you scratch a little bit of head at home. Now look at here quickly. That I mathematically show here, right? You can also do it here. Look at there. As you showed, hey, look at here. As you showed, this is your V. At that point you showed, correct, in the vector polygon. And now have a look. From here, BD is approximately 1/3 of BC. So you go, if this length is your VB, another one third, you increase that direction. You increase from, you see this one is a half. So you bring here up to that point, you show another line with from here with a different color up to that point arrow, that will be your BD. And your F is a midpoint of your BC, right? You show here your F and you show another line with a different color up to that point is your BF. Your BF. So you can show it here. Or if you say, no, Professor Firoz, I'm already tired, I don't know which way I can make mistake. So you use this beautiful formula. But if I am here in your position, I will not do calculator at all, because you know all these things, why I do all these things. I will be doing on this line. And my life is easy, quicker, gone. I will be only doing these things to cross check. I will be only doing this calculation to cross check. In my exam, in my entire life, I always wanted to make sure my answer is absolutely correct. Absolutely means not 100%. I mean the value can be here and there a little bit, small fraction, but value is coming close to it. And I always did 2 methods, sometimes 3 methods, if time permitted me. And when I went to the teacher said, oh God, this student, not only one method he showed, he even showed another method. So always teacher get a good impression. This person understand it, what he's doing, or she is doing. Okay. Now, is it clear? Okay, we'll have a little break, and after that, we will do quickly the acceleration, and then I'll move on to a little bit more harder one example, because I want to do such a way of the graphical part, because my whole intention is to spend a lot of time in graphical part, because